our first video on COVID-19, we talked about the SEIR model, in which at any point in time, every individual is either susceptible, infected, or recovered. Now we're going to talk about sort of the more sophisticated model, which I think most epidemiologists use a modification of. The susceptible, exposed, infectious, recovered, susceptible model, or SEIRS model. So basically what happens in this model is you don't go right from being susceptible to being infectious. You're exposed first, and then after a certain number of days, you'll become infectious. And once you recover, you can lose your immunity and become susceptible again, and we'll include births and deaths in our model in theory. So let's look at how we have to modify what we did in the SEIR model. So we assume there's N people again, and there is a birth rate mu. Okay, so in a given day, the number of births will be mu times the number of people. So I guess the number of people could go down due to the deaths, but we'll assume that stays fixed. Okay, and then a fraction mu of people die each day from non-disease causes. That would sort of keep the number of people sort of stable in the population. Now we're going to assume that mu is 0, so there's no births coming into the system, and the only way people die is from the disease, to keep it simple. We're not going to worry about the birth rate there, but the epidemiologists, of course, worry about this. Now remember, in the SEIR model, beta, which was pi times k, okay, pi was the fraction of the time of contact between infectious and non-infectious would result in somebody getting sick, and k was the number of contacts per infectious person. Okay, beta times the infectious times the fraction of people who are susceptible would go to infected, but now they go to being exposed. And how long do they stay exposed? An average of 1 over sigma days. We'll assume sigma is 1/7. Okay, there. So basically 1 over sigma would be 7 days they stay exposed before they get infectious. You can change those numbers over here if you want. Okay. Now, recovered people lose immunity in an average of 1 over omega days. We'll assume that's a long time. It can become reinfected. We'll assume people can stay immune for a year. So 1 over omega would equal 365 and a quarter days. So omega is 1 over 365 and a quarter. And infected people, unfortunately, can die at a rate alpha. Now, when I'm taping this, recording this, it looks like about 0.4% is actually the infection death, the IFR, the infection fatality rate, because even though there's 8 million cases in the US recorded, there's probably 50 to 60 million cases, most people think. And then when you work that out, you do 200,000 over 50 million, you get 0.4%. Okay, and that includes the death rate that was higher at the beginning and is probably lower now. So we assume 0.4% of the infected people die. Of course, many people have long-term COVID effects, which are horrible, I'm sure. Okay, so then the death rate would be 0.004, but that's per day infected, so you have to divide it by 14. So that's our death rate there, right there, the 0.004 divided by 14. And we'll go through the equations here, but I should mention that the epidemiologists souped this model up basically by having multiple age groups, heterogeneous transmission rates, and probably doing other things that I don't know a lot about. But so let's look at the equations for the susceptible people on day t+1, the exposed people, the infected people, and the recovered people. And then here are the formulas that we used. And to go down to the chart, the right-hand part, again, this is scattered smooth line with markers. The right-hand axis is the number of deaths, and we get this 2.5 million deaths if we run this through 1,000 days, a couple of years, and that's what was sort of bandied about by Imperial College, and even the president mentioned that. Basically, we could have had 2 million deaths, and so putting in these parameters, we get there could have been 2 million deaths, I should say, 2.5 million deaths, not 2,000 deaths. Okay, so now let's look at basically the 4 equations that define the dynamics of the model. Who's susceptible at day t+1? You have the people susceptible at day t, plus you have the births, mu n. Okay, and then you have minus beta I t, infected the previous day, times susceptible, divided by the total number of people. Those are people who will move now to exposed, not infected. Okay, and then you're going to have basically people who get susceptible because they were infected and they lose their immunity. That's that omega thing here. Okay, and then you're going to have people who die of other causes, but we're going to push that to be 0. Now, who's exposed at day t plus 1? The people exposed at day t plus basically these people here who basically got pre-infected, okay, they got the virus and now they're exposed, okay, and then people who were exposed, remember with that sigma, they can go to be infectious, okay, in an average of 7 days. So that's what happens to those infectious people from the previous day. Approximately 1/7 of them become infected. And then basically we'd have the people who die, but we're not going to, who were exposed, but they might die from something else. But again, we're assuming that's 0. Now, who's infected on day t plus 1? The people infected on day t, okay, plus basically a fraction. In our case, we're assuming 1/7 of those exposed moved to be infected, okay, and then basically the gamma here is going to be the recovered. So roughly 1/14 of those infected will recover, okay, and they basically they'll come down here, and then basically we'd have people dying of the other causes, and then basically the alpha here is the people who died from the virus, okay, and that will give us the deaths, unfortunately. Now the recovered people at day t plus 1 are the recovered from the previous day, okay, then you'll add a fraction. In our case, we'll assume 1/14 of the infected people. Again, we put in R0 equals 3, and basically R0 equals 3 lets you figure out basically what your beta is. Gamma times R0. And so basically a recovered people would be at a given day, the recovered people from the previous day, okay, plus basically a fraction of the infected people from the previous day would recover, okay. Then basically you're going to lose those people who recovered who become susceptible again, rate 1/365 and then basically these would be people who die from other causes, okay, but again, we're not going to have any of that. So that's right here, I should say. So we have basically the recovered at day t plus 1, again, the recovered at day t, okay, plus the infected people who recover. And we have people basically, we're going to lose the people who lose their immunity, and then the recovered people who die from something else. And then here's how those equations shake out. And then you can just follow it down. We just start with one exposed person, and we have a population of 350 million people, approximately the US. And basically, we just let these formulas rip for 1,000 days, almost 3 years. And basically, here's what we see happens. Okay, we can see we go to over 2.5 million deaths. And we can see that there are waves, like they talk about a second or third wave. And so basically, we look at the susceptible. Okay, it drops down, but then it comes up as people lose their immunity, drops down, and then it comes up again. So basically, you can see how this model is a much richer model. And if epidemiologists can fit the parameters of this model well, they can sort of predict what's going to happen. But again, we can control R0 somewhat by our behavior, by social distancing, wearing masks, going out less, or going out to places that have not having weddings with a lot of people or gatherings, weddings or tragically funerals with a lot of people. We can reduce R0 and help stop the spread, as I guess the phrase comes from the CDC. So I hope this video has been useful, and the last one useful in understanding the basic models that epidemiologists use, and also how easy it is to implement these models in Excel. Now, in the next few videos, we're going to concentrate on looking at the actual COVID data. Not that reliable, to be honest, because it's only people who took a test and tested positive. Not everybody gets a test, and the tests aren't perfectly accurate, and show you how to use pivot tables to basically summarize US data and data around the world.